Okay, in this portion, what we are going to do, we are going to study about the infectious diseases. So this is a flu season. So a lot of people in here in Pullman, in other places, they are going for vaccination so that they don't get the flu. So let us look at a case of two little towns. So I want to call the first town, maybe that's your town, and call that Cougarville. And maybe there's another town, something like 300 miles away from here, from Cougarville, call that the Purple Land. So in this Cougarville, there are, let us say, 10,000 people. And in Purple Land, there are 12,000 people. And they know this flu is coming. So the people in Cougarville are preparing so that they don't get infected. So there is preparation for vaccinations. All the doctors' offices are giving free vaccines to people who go there. And you can also get vaccinations in stores like Safeway and Walmart. So people are getting vaccinated. At the same time, even in the Purple Land, a similar thing is happening. And the people, the health officials in Cougarville, they are monitoring the number of people who are getting vaccinated. At the same time, they are trying to see whether anybody is getting sick. And at one point, they determine there are 2,000 people vaccinated, and there are 100 people who are infected, who have got the flu. So there's a little bit of panic among the health officials because they think, we have 10,000 people in the town and only 2,000 people are vaccinated. So they are worried the infection is going to spread. But then comes along a guy who lives in Cougarville. I want to call him Mr. Smart Alec. And he says, based on some calculation that he did, if you had 2,000 people vaccinated, the flu is not going to spread. People don't believe him, but he is so adamant that that's going to happen. At the same time, the guys in the Purple Land, they are observing what's happening in Cougarville. Unfortunately, Purple Land does not have a Smart Alec. So what they do is they look at what's happening in Cougarville, and they see there are 2,000 people vaccinated. So the people here in Purple Land, they say, okay, we will have 2,500 people vaccinated. If you have 2,500 vaccinated, then the flu will not spread here also. Okay? So that was the argument the Purple Land people are making based on what they see in Cougarville. Again, in this case, you have 100 people who are infected. So the health officials in Cougarville, now they are monitoring what's happening with the infection. So if I want to call a graph with the x-axis being time, and let us say the y-axis being number of infected people, from the time you started, in the case of Cougarville, at the time you started, if you call that time 0, there were 100 people infected. Then they try to monitor what happens every other day in terms of time. And what they notice is the number of infected people seems to drop. So Mr. Smart Alec was correct. With just 2,000 people vaccinated, the infection did not spread. It started to die off all by itself. So this is what happens in Cougarville. Now let's see what's going to happen in the Purple Land. So again, there you had 100 people infected at time 0. But when they monitored the number of infected people every other day, what happened there was the number of infected people started to increase and then peaked then it came down to 0. The infection did not die out all by itself. It went up and peaked, then came down. So why did this happen? So what did this Mr. Smartalek know that these guys in Purple Land didn't know? Okay? So this is where simple mathematics will come to help you. What is the math behind it? In order to start, let us look at the total population of the town. Now what we are going to do is to divide this population into 3 subpopulations. The first subpopulation is a group of susceptibles, that is, people who can be infected. Then the second subpopulation is going to be the infected people. Then the third one is going to be the people who I say are removed. That is, people who got infected and then got immune, or maybe people who got infected and the health officials in the city decided to isolate them so that they don't mix with the susceptibles. So people are removed in different ways. And also the people who are vaccinated. So they are not susceptible, and so they are not going to become infected again. So these are the 3 subpopulations. So now let us say at any given time we have some susceptibles, some infected, and some removed. So to use a notation, I want to call the susceptibles S, the infected I, and the removed R. So if I write it here again, you have S, I, and R. So these are the subpopulations. Now if there are some infected, there's going to be some kind of contact between the infected and the susceptibles. So whenever there is contact, it is possible that some of the susceptibles will become infected. Not all the time, but sometimes they will become infected. So if there is contact here, that's going to create possible infection. Okay? Then if the infection happens, the next time, let us call this time 0. Then let us say, look at the time after 1 unit. The 1 unit could be, in this case, you are looking at the number of susceptibles and infected and the removed, let us say after 2 days or after 1 week or whatever the case may be. So the unit of time may depend on the problem you are looking at. So when you look at the susceptibles here, after a unit of time, it is not going to be that S. It's going to be that S, then minus how many people are lost to infection. So that's going to be, if I want to write it, it's going to be some alpha times S times I. So the S times I comes about because of the interaction between the 2 populations. So you are multiplying those 2 populations. And the alpha comes about, this is the infection rate, because even if you interact with the infected person, you may not get infected. So there's a probability that some of the people will get infected and some of them will not. So the infection rate comes about from those kind of probability. Now what will happen to the new I at time unit 1? The new I is going to be I. Now these are the people that are lost from susceptibles. Now they become infected, so they will come into this group. So it's going to be plus alpha Si. But then some of the infected people are going to recover. So they will move into the site what I call removed. So it's going to be how many people are going to be removed? So I can call that some minus beta I. Okay, that beta is the, you can call that the removal rate. So this tells you how many of the infected people are getting recovered and become immune to the disease. So now these people are going to join the removed group. So that's what you have. So if you want to write it in a more general form, where if I want to call S at time 0 as S0 and I at time 0 I0 and R at time 0 as R0, then in a similar fashion, if I call the S at time 1 as S1, now S1 is equal to, based on what we have there, S0, that was what we had before, minus alpha S0 I0. And I1, the infected at time 1 is going to be I0 plus alpha S0 I0 minus beta I0. Then the new removed, that is R1, is going to be R0 plus beta I0. So that is the mathematical, a simple mathematical model to describe how the disease spreads in this little town. Now, if I want to make it even more general, because this kind of process is going to continue to the time unit 2, then it will go to time unit 3, and so on. So when this one from time unit 1 goes to 2, what will happen? This S1 will become S2, I1 I2, and R1 will be R2. And all the zeros on the right hand side, like S0 will become S1, and the I0 will become I1, and so on. Okay? So if you want to write this in a general form, I could say this is S k plus 1, I k plus 1, and R k plus 1. And on the right hand side, all the sub indices will be simply k. So if you look at this, it tells you the population for susceptibles, the infected, and the removed. On the right hand side, they are for the time unit k plus 1, and they are based on what you have on the right hand side. That is what the population was at the time unit k. So now let's do some simple manipulation with these equations to see what happens. So all I'm going to do, I'm going to look at only this portion. So what is that portion? That portion is the change in infected at any given time. So the change in infected is given by alpha sk ik minus beta ik. Now if I take alpha ik as a common factor, then we can rewrite this as alpha ik times parentheses sk minus beta over alpha. And I'm going to call this beta over alpha, which is a constant. Remember, beta is the rate of removal, and alpha is the rate of infection. So this is a constant. I'm going to call that by a new name, call that S bar. So I could put that into the equation and say alpha ik minus sk minus S bar. So that's the change in infected at any given time. So when we look at this, for example, let us say at time 0. At time 0, that equation will look like alpha I0 times S0 minus S bar. Okay, so that will be your change in infected. So here again, remember, alpha is your infection rate, so that is a positive number, and I naught is the number of infected people. Again, that is a positive number. If S0, so now we are looking at this term within the parentheses, if S0 is less than S bar, what happens? If S0 is less than S bar, that term in the parentheses will become negative. So if you look at the product here, alpha is positive, I0 is positive, and S0 minus S bar is negative in this case. So when you multiply all that, you get a negative number. So what that means is the change in infected is negative. So you started with the infected number of people I0, but when you go into the next time level, your I1 is going to be I0 minus something. Because minus something because your change is negative. So your infected number of people is decreasing. Okay? So this is the kind of calculation Mr. Smart-Aleck did to come up with the answer. Because all you have to do is to have your S0, the number of susceptibles at the time 0, that should be less than S bar. Okay? So in the case we were looking at, that is in Cougarville, based on the data he had, Mr. Smart-Aleck knew that alpha, the rate of infection, was 0.0001. And also he knew that beta, the rate of removal, was 0.8. So if that's the case, the S bar is going to be beta over alpha. That's going to be 0.8 over 0.0001, and that will be equal to what? It's going to be 8,000. So all you need is the number of susceptibles at time 0, that is S0, should be less than 8,000. So if it is less than 8,000, the infection is going to die out. Okay? So let's go back and look at this. So at time 0, we know that S0, the number of susceptibles, plus I0, the number of infected, plus R0, the number removed, should be equal to 10,000. That's the population of Cougarville. And we knew in that particular problem that I0 was 100. Then in the case of, in this analysis, we know that S0 should be less than beta over alpha, which is 8,000. So let us say we want to have an S0 which is 7,900, which is going to be smaller than S bar, which is 8,000. So if that's the case, here S0, let us put 7,900. So your S0 is 7,900, I0 is 100. So from here, what do you get for R0? So when you start off the process, if you have 2,000 people removed, then the infection is going to die out. So that's why Mr. Smart-Aleck said, if there are 2,000 people vaccinated, we are okay. And that was true.